thank you all for inviting me here. It's really a pleasure to be here. I'm Giovani Aricò. I'm a PhD student in the group of Raul Angulo in Donostia, in San Sebastian, in the Basque Country. So here, and today I'd like to speak to you about some of my recent works in collaboration with, mainly with the Cosmology group in San Sebastian. So here are like some of my collaborators. And the outline of the talk is the following. So I'm gonna start with a very brief introduction of large-scale structure surveys. And then I'm gonna present the BACCO Simulation project, which is the main project we are developing in San Sebastian. And then I'm gonna go to modeling, to the modeling of the matter distribution for large-scale structure. So a first part will be in modeling dark matter, or better, gravity-only matter. So like just considering the action of gravity. And in the second part, I'm gonna speak about modeling baryons, so gas and stellar distribution. This was a big chunk of my PhD. And finally, I'm gonna speak about emulators and our kind of emulators. These are neural network emulators and how to use them to speed up analysis for large-scale structure. Large-scale structure surveys are nothing but maps of the skies. So we humans have made maps since very ancient times. Probably one of the first was this Nebra sky disk in Germany, thousands and thousands of years ago, which you can see like the moon and the stars and everything. But also in ancient Egypt, they were making star charts. They were using it to make calendars for agriculture, like to have like a good calendars for when like planting stuff and when to get stuff, but also in the afterlife to guide the pharaohs like in their trip around the sky, like in the afterlife. And nowadays we use these sky maps in order to get information about the universe and how it works. So we have different kind of sky maps. For instance, here you see like the cosmic microwave background maps. And we have mapped it with different satellites. And as you can see from the 90s and ICCUB and to WMAP and Planck, the resolution of these maps is getting higher and higher. So we're getting more and more information out of that. And this is very high redshift, so probably the highest redshift we're gonna ever get. But there are also some other maps that map the low redshift. So like the large structure that is local. And it is, for instance, the BOSS galaxy surveys that you see here. Every point of this map is a galaxy, right? We have millions of that. And you get also different kind of maps, for instance, the weak lensing maps that are made by surveys like the dark energy survey or the kilodegree survey or HSC survey. And this, by mapping effectively the galaxies, they can in some way retrieve the total matter distribution that is projected into the sky. And these are some of these current survey here, but in the next years, some other surveys are planned. For instance, the Euclid mission or the Vera Rubin missions that are gonna get this galaxy and weak lensing surveys more and more accurately. So they're going to map a large part of the sky. They're going to have more accurate position, more galaxies, so way more information that we have to process in order to get cosmological parameters. So how do we extract cosmological information from large-scale structure surveys? So the observable we have are just few observables. So we have galaxy position. We measure the angular position of this galaxy in the sky. We measure the redshift, so either with spectroscopy or photometry. And for weak lensing surveys, we measure also the galaxy shapes. And from these few observables, we have to model several physical processes, for instance, galaxy clustering or the cosmic shear. We have the baryonic acoustic oscillation peaks or the redshift space distortion. We can have galaxy clusters and do the physics of these galaxy clusters. Different kind of processes. And in order to get the cosmological parameters, we have to compare the observation with our theoretical predictions. But since these are very complex systems, what we do in general is to lower the complexity of the analysis by using summary statistics. So in general, what we do is to use 2-point statistics like correlation function of its Fourier counterpart power spectrum, or we can go to higher order statistic in order to try to get more information, for instance, with the 3-point correlation function or the bispectrum. So what you observe in general is something like close to this in the left panel. So we have the galaxy correlation function get from the SDSS galaxies by Eisenstein and others in 2005. So you see that this correlation function goes like a power law, and then at very large scales, you have like this nice bump that is the BAO, the baryonic acoustic oscillation peak. And these black dots are what you measure by the galaxies, and these colored lines are the models. So how do you model this? In general, what you do is to model the total matter distribution in the universe, and then assume that your galaxies are biased tracers of this field. And to model the total matter distribution, you can use linear theory, for instance, linear perturbation theory. So, but this assumes that the perturbation of your density fields are very small, are linear. So, and this assumption only holds at large scales or a very high redshift. So when you go to small scales or low redshift, this breaks down. And in this regime, you can try to further model with other theories, for instance, Lagrangian perturbation theory or effective field theory of LSS. And you can get to model maybe like here is the power spectrum, so the Fourier transform of the correlation function. And you see the linear matter power spectrum is in blue, whereas in the red you see the Lagrangian perturbation theory, and this is can get up to scale 0.2 maybe. With effective field theory you can get to K0.4, but then also this breakdown. And to model the very small scales, for instance, the K of 10 h/, you need to use n-body simulations. But you wish to model these small scales because there is a lot of cosmological information in these scales, in theory, because the number of modes grows as k to the cube. So where you go smaller, you should gain much information. But the drawback of n-body simulation is that they are very expensive. So in order to do a proper analysis, you need a very large volume because of the statistical power. You have to get a volume that is statistically consistent with your survey. And you need, if you want to model small scales, you have to have a high resolution in order to model them. And so this is a very large dynamical range that you need to model with your simulation. This can take millions of CPU hours. And then there are further complications. There is like you have to spanning a large cosmological space if you want to use them for the cosmology inference, right? So you cannot just have a set of cosmological parameters because you don't know them. So you have to vary them and you need so many simulations that span your cosmological space. And then there is further the galaxy bias that you have modeled, because in the case of gravity-only simulation, you have just the action of gravity, so you don't have galaxies, and you have to put them on top of your matter distribution somehow. And another problem can be the baryonic physics, so the gas distribution here that can modify the overall total matter distribution. And for instance, you can both model galaxy and baryon physics coherently with hydrodynamical simulations. But here you get even larger running times, so they are way more expensive than n-body simulation, gravity only. And a further problem can be that the uncertainty on the baryonic physics and subgrid processes of these hydrodynamical simulations. For instance, in this plot, we are showing several hydrodynamical simulations that are state-of-the-art, like Hegel, Illustris, and Illustris TMG, and few sets of the Bahamas suite. And what this plot is comparing is the hydrodynamical run of this simulation and its counterpart, gravity only. So you run basically the full hydrodynamical simulation, and then you run the same simulation, but switching off the baryons, just taking the cosmological parameters. And then you do the ratio between this power spectrum and this is what is plotted here. And you see that overall, all the simulation have the power that is suppressed by the gas distribution. So the physical picture here is that the gas is pushed away by, for instance, AGM feedback or the baryonic processes, and you have less power at these small scales. But the problem is that different hydrodynamical simulation predict very different suppressions. So you have like the most extreme that is Illustris here, and like Eagle that on the other hand doesn't almost predict a suppression. There is almost a 35% in difference between these two. And so since you don't know a priori which one is the correct model, you should not only span the cosmological parameters with these simulations, but also the baryonic parameters. And a similar picture, we get it going to higher order. So this is the bispectrum, and you see also in the bispectrum, this simulation have very different predictions. And I'm focusing also in weak lensing surveys. So in this kind of surveys, what you measure is the distortion on the ellipticities of galaxies. So what you do is to assume that the galaxies have kind of random orientation in the sky. And when observing very distant galaxies, you observe a distortion of their shape caused by the large-scale structure that the lights cross in its journey toward us. So these ellipticities will have a small correlation between them caused by the projected matter density field. And this is the total matter density field, so like matter, gas, everything. And this is a very small signal, so it's kind of 1% signal, but it is well measured by current surveys, for instance, the Dark Energy Survey collaboration. And here we show the cosmic shear correlation functions that the Dark Energy Survey released a couple of weeks ago, maybe 1 week ago. So it's very recent. And so you see there are different beams here. So what you do is to split the galaxy distribution in different redshift beams and cross-correlate each of the beams. And you have two different correlation functions. There are plus and minus. There are different directions in the sky. And you model it basically by integrating the power spectrum, so the total matter power spectrum here, integrated in redshift or in co-moving distance. And as you can see, though, one of the problems you have in these measurements is the uncertainties given by baryonic physics. So the baryonic effects enter in this matter power spectrum and doesn't allow you to model the small scales. In these measurements here, you see the gray bands. So this gray shaded area are measurements that are discarded by the DS collaboration. And these are discarded because of the uncertainties between, of baryonic effects. So as you can see, like in this correlation function, almost most of the data is just discarded because you cannot model it. So this is kind of a problem that is plaguing this kind of analysis, and that we want to somehow tackle. And so it was shown that if you just ignore this baryonic physics, you can get to very, very biased results. So for instance, in this study by Ore Schneider and others in 2020, they have a Euclid-like setup, because of course, like when you get more and more accurate, so you get more and more bias, right? So for Euclid, this is going to be a bigger problem with respect to what it is now for the Dark Energy Survey. So in this kind of Euclid setup, you have that by just measuring the shear with ignoring baryons, you have these black contours. So here you have the cosmological parameters, omega matter, omega baryon, sigma 8, etc. And you get these black contours. But if you include baryonic physics, you have these blue contours. So you can get biased at more than 5 sigma. So one of the things you can do is just to ignore the small scales. So in order to, that are the ones that are mainly affected by baryons. And doing this, in this case, you would get these gray contours. So you're gonna lose most of your constraining power. And it is shown also in these plots that there is basically Fisher analysis on the constraints given by the matter power spectrum by going to smaller and smaller scales, from a Kmax of 2 h over megaparsec, the blue, to a Kmax of 5 h over megaparsec, to the red. You see as the contours on your parameters shrink and shrink, going to smaller scales. And so we want to tackle this problem, and using like our own approach, that is the BACCO Simulation project. So this project used highly accurate prediction for the distribution of mass, galaxy, and gas in the universe. And to do that, we ran few high-resolution simulations. And the idea is to span the cosmological space with rescaling algorithms. So in order to not have this problem that we had to run hundreds, thousands of simulations in order to span the cosmology, we just run few, and then using these algorithms in order to span the space. So how does cosmology rescaling algorithm work? So let's assume we have run a simulation and with a given cosmology, there is, for instance, omega matter 0.3, and then we run another simulation with omega matter 0.1. As you can see, these two simulations are pretty different. So one is like the matter is more concentrated, is more collapsed. The other, the matter is more distributed. So let's assume that we take the first one with omega matter 0.3 and we apply some scaling into its size and time. So with size, I mean, we scale all the box and all the particles to make it, for instance, larger, right? And in time, I mean, we pick a different snapshot of the same simulation. So this was Z0, like redshift 0. We go to redshift 2, for instance. And as you can see, like by picking these two transformations, the two density field now with omega matter 0.3 and omega matter 0.1 are very similar. So how do we find this transformation? We minimize this function. That is basically saying that we are minimizing the ratio between the linear, the amplitude of the linear matter fluctuation between these two different cosmologies. So basically, we find this S factor, this is the size of the rescaling of the box, and this redshift star, that is basically which snapshot we have to pick in our original simulation in order to rescale the simulation and to get another cosmology. And we show that this approach can be very, very accurate. So in Zennaro and others in 2019, we have extended this approach in order to also have neutrino masses. So you basically can run your lambda CDM cosmology simulation, and then afterward, in post-processing, you can add the neutrino mass effect. So you can have like simulation as you would have run with a neutrino mass of 0.06, for instance, electron volt. And this is going to be very accurate. So here you see the ratio between the power spectra measured by directly on a simulation or on a over a rescaled simulation. And here is we see that we get a 3% accuracy in overall in the matter power spectrum, also in the halo power spectrum, in the sub-halo power spectrum. And we extended also this approach in Nondaro and others in 2021 in order to basically to take into account the non-universality of halo mass functions in order to have more accurate results in the scaling the halo mass function. And now we get 2% halo mass function from this rescaling. And so we can use it in order to span our cosmological simulation, our cosmology space. So we have run 3 simulations, very large simulation, 2 gigaparsec of size, 4,300 cube particles. So this is very high resolution. And we pick 3 particular cosmologies that we dubbed Nenia, Nari, and Vilia as like the rings of power in Tolkien mythology of the Lord of the Rings. And we pick these cosmologies in order to optimize the cosmology rescaling. So what I mean by this, like, let's assume that we have a cosmology space in omega matter sigma 8, and we put a simulation like in the center of this cosmology space. So when you will have to rescale your cosmology to each of the points of this cosmology space, you're gonna have a given error in the scaling. But then you can try to minimize this error over the space, and you will see that your simulation is gonna move toward high sigma 8. This is because the scaling prefers to scale from high amplitude fluctuation to low amplitude fluctuations. And then we can basically wonder how many simulations do we need in order to get a threshold error, so like a maximum error. And we decided to run initially 3 simulations with these 3 cosmology here in order to have like a very accurate scaling over all the parameter space. And so this is the 3 simulation with the power spectrum you see are very different. Power spectrum, correlation function, and Elo mass function. And lately we run even a 4th one with the 1 after the ring of power of Sauron. And so we have in total 4 simulations to cover all the cosmology space. This is all just gravity only, right? So we have somehow to add baryons on top of this gravity only simulation. And now we do it is using the Baryonic Correction Model. So this is an algorithm that was developed originally by Ole Schneider and Romain Tessier in 2016. And this is basically how it works. So you have your snapshot, your simulation, this gravity only is already run. You take your snapshot and you consider all the halos inside your simulation. So once you have your halos, you can model their density profiles. For instance, like a Navarro-Frenkel White, there is this universal density profile that was found in simulations. And once you have your density profile of the simulation, you can add new density profiles that should model different baryonic components. For instance, you can assume that there is some gas in hydrostatic equilibrium inside the halos and model its density profile with some assumption, like a polytropic equation of state. You can assume that a given fraction of the gas was expelled from the halo by some AGN feedback. You can like assume a given density profile also for this gas. And then you can put at the center of your halo a galaxy, right? Because, or like several galaxies, like satellite galaxies, and model also this density profile. So in the end, you're going to end up just from having one Navarro-Frenkel White profile to have a bunch of baryonic components. And you can go and sum all these profiles in order to have a total baryon corrected profile, let's say. And once you have this profile, you can work out a displacement field that you have to apply to your particles in order to go from the original density profile to this new density profile. And once you have applied your displacement field, you're gonna see that your particles follow the new density profile. But even if these assume a spherical symmetry, this full proceedment is not really spherical symmetric because this preserves the original shape of your halo. So if your halo has originally a given shape, it's going to be overall preserved by this proceedment. And this model has just a few physically motivated parameters. A basic implementation of only 4 parameters, but can get up to 7 with different components like galaxy satellites or gas that is reaccreted onto the halo. And these 4 basic parameters are, for instance, MC, that is a parameter that is regulating the quantity of gas that is retained in the halo. And as you can see in this plot, for instance, where is the suppression in the power spectrum varying this MC parameter. When you have less gas inside the halos, you have the more suppression in the matter power spectrum. Or there is the zeta parameter that is regulating how far the gas is ejected by the GN. As you can see, like the farther the gas go, the largest the scale affected by baryons. And in SEM1 is regulating somehow the mass of the galaxy inside the halos. As you can see, the highest the mass, the largest the mass, the more power you have at small scales. And then we have this beta, that is the slope of the gas fraction as a function of the halo mass. As you can see here, is tilted. It tilts the suppression. And once we have also all these analytical density profiles, we can wonder like if they are a good fit, for instance, on the hydrodynamical simulations ones. So we fit the density profiles of the illustrious TNG simulation, and we fit both the stellar profiles and the gas profiles. So the stellars are the kind of orangish one, and the gas is the blue. And we fit it in 3 different halo mass bins. As you can see, the fit is quite accurate. And then we fit directly the clustering of these hydrodynamical simulations. And we fit both the power spectrum and the bispectrum. In particular, we fit the reduced bispectrum. That is, we use a equilateral configuration for our triangle. So the reduced bispectrum is given by the bispectrum over 3 times the power spectrum square. And we fit separately in 3 different redshifts, so redshift 0, 1, and 2. As you can see, we can reproduce the clustering of Eagle, Illustrious, Illustrious 3NG, and 3 different Bahamas at very accurate precision. So we have 1% in the power spectrum and 3% in the bispectrum. So this is quite accurate technique. And we also retrieved a correlation that was found initially by using hydrodynamical simulation by Van Dalen and others in 2020. So what they found is a correlation between the suppression in the power spectrum and the fraction of baryons inside the halos. And this is basically showed as the dashed line here in this plot. And as you can see, by using our Baryonic correction model, we found these color symbols, right? The circle and the diamonds, and these are very much in agreement. There is a bit of disagreement for very extreme models where almost all of the baryons are expelled. And we found also a similar correlation in the bispectrum. So with a different kind of dependency from the power spectrum, but a very accurate, very tight correlation between the bispectrum and the baryon fraction. So so as I told you, like this, all this approach can be a bit expensive computationally. So like to apply this Baryonic correction model plus the rescaling into our large simulation can take few minutes. So this is basically doesn't allow you to do direct cosmological inference. And what we do to do this inference is to build emulators of our summary statistics. So emulators are just interpolators of a costly function over a given parameter space. You can have emulators of with different methodologies, for instance, Gaussian processes or polynomial Gauss expansions. But we decided to build our emulators with neural network. And this is because we found that when you have like a large data set, these artificial neural networks are cheaper to run. And since we can, with our cosmology scaling, for instance, or our Baryonic correction model, have sampled very well the space, then we decided to use artificial neural network. So briefly, a neural network is a system that it is based of a unit, processing unit called neuron. So these neurons are organized in layers. You have a first layer that is the input layers. So usually you have your parameters, cosmology parameters or baryon parameters or whatsoever. And then these go to several layers that are called hidden layers, okay? And finally, you have a layer called output layers that are gonna output your prediction of your summary statistics, for instance, the power spectrum. And so each of the neurons of one layer is connected with all the neurons of the previous layer and the next layer. And in each of these connections, a weight is applied. So you apply a linear weight, and then in the neuron, you apply a nonlinear function. This is called activation function. So basically, you apply a linear weight, nonlinear function, linear weight, nonlinear function. And the purpose of this network is to optimize the weights in order to minimize a loss function. So basically, you define a loss function in order to kind of measure the discrepancy between your prediction, the prediction of the network, and the reality. So you have a training set, so-called. So when you have a bunch of models pre-computed that the network can take in order to compute this loss function, and these weights are going to be minimized to get the best prediction over that training set. So there is this backward propagation. There is the network computes the derivatives of the loss function with respect of each of the weight. And once you have the derivative, you have you can descend the gradients in order to minimize these weights. So bottom line of all this is that you have a lot of these weights. So like a network can have millions of weights, and you optimize them in order for your prediction to be the closest possible to your training set. And we have built the first emulator. There is a nonlinear matter power spectrum emulator. So what we really emulate is the so-called nonlinear boost function. There is diffraction between the nonlinear matter power spectrum measured by our simulations and the linear one. We emulate this fraction because we find that the emulator is way more stable running by emulating the ratio and not directly the nonlinear matter power spectrum. And we find that, so we scale our main 3 simulation to 800 different cosmologies, right, at different redshift, so that in total we have 16,000 spectra. So our 8-dimensional space is very well sampled. And then we do this neural network optimization, and we get some accuracy on this nonlinear boost factor of 2% in the case of lambda CDM and 3% in the case of dynamical dark energy. And here you can see, for instance, the fraction of the power spectrum of our MODI simulation over the emulated one. You see it is like very accurate at both redshift 1 and 0. And we also compared this with different methodologies to get nonlinear matter power spectrum, like the popular HaloFit. And you see that the HaloFit in this case at redshift 1, for instance, has 5% off at K1. But we find better agreement, for instance, with the Euclid emulator, around 2% agreement between the two. And also good agreement with Engine HaloFit and the Mira Titan emulator. So using neural network emulator, you can speed up your analysis a lot. So just to evaluate the emulator takes 1 millisecond. But this means also that since we are emulating the ratio with the linear matter power spectrum one, so our bottleneck in this case is the time of execution of the Boltzmann solvers that compute the linear matter power spectrum. So if you use class, or CAM, in general, you get a power spectrum in 1 second. But using massive neutrinos, you can get to 7, 10, 15 seconds, depending on the neutrino mass. So since this is our bottleneck now, we decided to emulate also the linear matter power spectrum. There is anyway a very useful quantity for different kind of analysis. And so we can get, considering an MCMC of 100,000 evaluation, like just using the Boltzmann solvers, we would get 28 hours of running time, or with neutrinos 8 days of running times. But just using our emulator, the linear matter power spectrum, we would get everything in 100 seconds. So it is a huge increasing of time speed. And this linear matter power spectrum is also very accurate. So we defined for it two different spaces, cosmological space. And one is the standard space where also the nonlinear matter power spectrum was built. So this is more or less 10 sigma around Planck best fit. So it's very large parameter space. In this case, we get 0.3% accuracy at all scales. And we defined also an extended space that is more or less double the space in each of the parameters. And in this case, we tested very extreme models where all the parameters simultaneously are farther than 10 sigma from Planck best fit. And in this case, we get like still 1% accuracy in the emulator. So this is even with very extreme cosmology is accurate, is very accurate. And here we have, for instance, a zoom in the baryonic acoustic oscillations. So the solid lines is class, and the dashed lines is the emulator. And I mean, you cannot distinguish the two of them. So I think it's a good sign. And this is basically 0.2% in these oscillations. And we checked if by using this emulator, you get bias results in a stage 4 survey, for instance, in a Euclid-like setup. So what we did is to compute the shear power spectrum. So just integrating redshift the matter power spectrum with some lensing kernel. And we did it both using directly class and our emulator. And this is the contours we get in different cosmological parameters. So the black is using class, and the red is using the emulator. And you see, we find basically the same contours and very similar posterior distribution function for the parameters. So we conclude that you can use these emulators for this kind of analysis, and it's going to speed up your analysis a lot. And in the end, we also built a baryonic emulators. So in this case, we have 15-dimension space. So it's a huge space of both cosmological parameters and our full baryonic correction models with 7 different baryonic parameters. In this case, we emulate the baryonic boost factor, or the fraction of the power spectrum with the baryonic correction model over the power spectrum just gravity only. And we built our training set by scaling each of our simulation in cosmology and then apply a different baryonic correction model. And we built our emulator that is accurate at 2%. And with this emulator, for instance, we can try to fit all the hydrodynamical simulation we could get. These are a set of 74 hydrodynamical simulations that include the Bahamas suite, the Cosmo Owl suite, the Owl suite, and then Illustris, Eagle, Horizon AGN, everything we could get. So this is very different baryonic feedback, as you can see. So you have 40% different power spectra. And with our full model, we can fit them all at 1%, basically. And then we tried also to try to strip down our model to use less parameters and to see if the fits were degrading. And we see that even going to 1 parameters, if we can get still good fit on these simulations. This parameter is like the quantity of gas that is retained inside the HELOS that we showed before, that is correlating strongly with the power spectrum suppression. And we did this more quantitatively using the ACCUB information criterion. So this is basically using the maximum likelihood estimation plus some correction due to the number of parameters used in the model. And like using this criterion, we find that most of the simulation prefer 1 or 2 parameters, both redshift 0 and 1. And these 2 parameters are related to AGN feedback strength. So like how much gas is expelled or retained and how far this gas is expelled. So basically, if you remember this density profile, this is basically the ejected gas density profile is a constant, right? And you can, with the first parameter, you basically change the normalization of this density profile. In the second, you change the distance of the cutoff from the center of the halo. And just to summarize everything, so this BACCO project is employing high resolution and-body simulation, and we combine them with cosmology rescaling and Baryonic correction model algorithms. And in this way, we simultaneously model the dark matter, the gas, and the galaxies in the universe. And to speed up the analysis of this, we provide emulators of the nonlinear boost factors, the baryonic boost factor, and the linear matter power spectrum. And we have also other emulators that I didn't speak of that are for the galaxy bias in a Lagrangian framework. And these are, I invite you to check the paper by Matteo Zennaro and others in 2021. And we have the nonlinear bias terms, and we have also the linear bias terms. And all these emulators are or will be publicly available at this website. So I strongly encourage you to go there and check our emulators, download them, play with them, and have fun. And I think I'm gonna stop here. Thanks.